Welcome to video lecture 4 for ECE 203. So in this lecture I want to go over first what we saw in the previous lecture, which was Euler's formula, Euler's identity. And I want to remind you guys how we can use this to show that we can add up a number of sinusoids at the same frequency and just represent them with one term. Okay? So the first thing you see written here, we saw this last time, right? This is just Euler's identity, this first line here. And all that's saying is we can represent a cosine plus j times a sine as e raised to j times the argument of what we put in the sine and the cosine, right? So of course another way to write this more simply is just e to the j theta cosine theta plus j sine theta. And we saw that that came from looking just at a Taylor series expansion of the exponential function, cosine function, and the sine function. Okay, so what can we use this for? Well, the first thing we can do is just say that we can represent this cosine just by taking the real part of e raised to the j times omega naught t plus phi. And that should just give us a times cosine of omega naught t plus phi. So that's this line here. Right? So we can use that to show one key property about adding up sinusoids at the same frequency. Okay? So even though they have different amplitudes and different phases, right? Here's the amplitude of each term in this sum and the phase of each term. Even though those are all different, what's the same is omega naught. Okay? So the frequencies are all the same. So the first thing we can do, right, is write this using Euler's identity, using that line that we've written just above, and taking just the real part of a complex exponential. And then we can take the real operator outside of the sum. Okay, it's this next line. All that's saying is the sum of the real part of a bunch of complex numbers is the same as the real part of the sum of a number of complex numbers. Okay, and then just factoring out this term here. It's factoring out this common e to the j omega naught t, we're just left with the sum of complex numbers. Okay? And that, of course, itself is just another complex number. And if we were to think in the complex plane, if we had a number of complex numbers added together, right, it's just really vector addition. So we're adding up these complex numbers, it's vector addition. This is the new complex number that we get, okay, drawn in black. And that, just for this example, that would be a e to the j phi. And it, of course, taking the real part of that, just using Euler's identity again, that's just a times cosine omega naught t plus phi. Okay, so what else can we use Euler's identity for? What other forms can we look at Euler's identity? Well, again, there's Euler's inverse formulas, right? Which are just for this cosine here and also down here for sine. And we saw these last time, but basically we can write the cosine function as the sum of two complex exponentials, also sine is the sum of two complex exponentials. So I just want to show you guys how you would verify these really quick. So this first one, cosine of omega naught t plus phi, if you wanted to verify this, all you would do is you just plug in Euler's identity for these complex exponentials on the right side here. So you'd have, on this side, you'd have 1/2 now times e to the j omega naught t plus phi. Okay, so that's just going to be using Euler's identity. That's just cosine omega naught t plus phi. Right? Now, plus j sine omega naught t plus phi. right? And then we also have this the second term here, adding that to the first term, right? So that's also 1/2, and now times cosine of omega naught, sorry, minus omega naught. Remember, there's a minus sign up here. Minus omega naught t minus phi, right? And that's also added to j sine of minus omega naught t minus phi. Okay, so I think everything should be accounted for here, right? We just took these two terms and expanded them out, these two terms, expanded those out using Euler's identity. Okay? And if you remember, the cosine function is even. So if we have the cosine of minus theta, that's equal to cosine of plus theta. So these two terms are actually, these first terms here and here, those are actually equal to each other, right? So really this is just, we can just switch this and make that a plus. Okay? We can't do that for the sine, right? The sine is an odd function. So sine of minus theta is equal to the minus sine of theta. Right? So if we want to change the sign here, in the inside of this, we need to cross this out and put a minus out front there. Okay, so with this you can see that these two terms cancel. This one's gone, this one's gone, and we're left with 1/2 cosine omega naught t plus phi plus 1/2 cosine omega naught t plus phi, and of course that just equals what we expected, right? Cosine omega naught t plus phi. Okay. So we could do the same thing for the sine, right? The only difference here is now that we'd see, after a bit of work, we write out Euler's identity in the same way. We'd see that the cosine functions actually cancel in this case. Okay? And then we'd just be left with, so it's a similar manner, I won't go through it step by step, you just be left with sine, again, omega naught t plus phi. After plugging in Euler's identity for this term and for this term, and noticing again the differences here, we have a j here, also a j here, and then a minus sign here. Okay, so that's how it differs from cosine. So then, excuse me, the last thing we saw was that we could just write another way we could represent the cosine function is just by taking the real part of the complex exponential. Right? I want to take a look at what happens when we shift signals in time. Okay? So included in this is what happens, what effect does phase, right, down here, what effect does phase have on the plot of a sinusoidal signal? So to kind of get a handle or a better feel for that, just imagine we have a signal x of t, and we're just going to say x of t is it's just going to be sometimes called the triangle function. And so let's just say it's 0, 0, 0, all the way out to 1, and then there's just a peak, a triangle. It's just easy to visualize. So that's x of t. Maybe we say 1 second, 2 seconds, 3 seconds, minus 1 second, minus 2 seconds. So if we shift this in time, and what I mean by that is if we define a new signal and we call y of t, say that equals x of t minus t naught. Okay. Let's say, for this example, t naught equals 2. Question is, what happens to this signal? What does the plot of y of t now look like? Well, you could, to figure this out, we could just start looking at different values of y of t. Okay. So let's start at y of t at t at 0. Okay. well, that should be equal to x at 0 minus t naught, which is just 2. So x at 0 minus 2. And that's going to be, of course, x of minus 2. Okay. So if we go back up to the original plot and say x at minus 2, should be right there, that's actually equal to 0, right? So that tells us that y of 0 equals minus 2, y of 0, which equals x of minus 2, just equals 0. Okay? That equals 0, and just know that point there. So then we say, all right, well, what happens now at y of, let's say, plus 2? Well, the value of y at plus 2, right, that's just going to be equal to x of 2 minus 2. And that, of course, is just equal to x of 0. And we go back up here, we didn't mark this, let's say that value is 2. That just equals 2, right? That equals this, that's exactly where this peak is. So we come back to the plot of y of t and look at the value of y of 2, right, which should be there. The signal should have a value of plus 2, right? And it's pretty easy to continue in this manner. We could do both look at y of 1, right? And we'd see that equals x of minus 1. Could look at y of 1.5. That, of course, is going to be equal to x of 0.5, right? And that's just equal to, well, it should be 1, right? Okay, so we got a couple points on the plot, and we can just fill it in from there. Okay? So this value t, right, this is just, this value of 2, that was just t naught. Okay, so we saw this effect of delaying the signal, right? So this is often just called a delay system. So the output, which is y of t, is just a delayed version of the input. We represent it just as follows. We'd say the output equals the input, time-shifted version, so y of t equals x of t minus t naught. And we can see exactly what effect that has. So if t naught is a big positive number, the signal is delayed by that big positive number. Okay, so it's easy to visualize, right, with this triangle, the triangle wave, or just with this triangle signal. It's a little tougher to visualize with sinusoidal signals. And we saw this last time, but we just want to see what effect, you know, how could we represent this x of t, now where we have a phase shift in the same form. So right here, we could think of this as maybe the time shift, right? Or since it's periodic, right, this could also be the time shift. Let's see that on the next page. All right. So if we just had, if we just plotted, instead of this time-shifted sinusoid that I'm showing here, if we just plotted cosine of omega naught t, right, without a phase shift, we just try and draw that in. Okay. So what is the value of t naught? Well, it's actually just written below here. it's T naught equals minus phi divided by 2 times pi times f, right? Where f is the frequency of this sinusoid. Okay, so how did we arrive at this equation? Well, if you remember, the cosine should have a peak when the argument is 0. So if we have a cosine kind of in standard form, it's cosine omega naught t plus phi, right? When this argument is equal to 0, then there should be a peak. All right. So at what time does that happen? Well, we just equate this thing to 0, and then we solve for t. And that gives us this value of T naught that's written right here. Okay. The next thing I want to talk about is now the spectrum of a signal. Okay. So we have a pretty good grasp of how we can plot sinusoids and how shifting them in time affects them and how we can relate that to phase. Now, just using these inverse Euler's identities, right, that we saw on the last page, we can write the cosine of 2 pi f naught t plus phi, which is written right here, as just the sum of two exponentials, right? Euler's inverse identity. So we can just think of that as a function of frequency now, right? So I just noticed I'm missing a t here, also here. Well, we can write this as this cosine is the sum of two complex exponentials. And that's going to allow us to just look at a plot of the signal in frequency as a function of frequency. And that's just called the spectrum of the signal. So we have that drawn exactly below. And on the x-axis here is frequency. On the horizontal axis is frequency in hertz. And on the vertical axis is just the value of the complex exponential at that frequency. So this again is called the spectrum of the signal x. So we wrote the signal x, which is just a times cosine of 2 pi f naught t plus phi. We just expanded that using Euler's inverse identity. Okay. And there were two terms involving two different frequencies, a negative frequency and a positive frequency. Right? There's the negative frequency and there's the positive frequency. You can look at the spectrum of that signal, right, which is just looking at the signal as a function of frequency. So again, on the horizontal axis, we've plotted frequency. On the vertical axis, we've plotted the leading coefficients here, right? This a over 2 times e to the minus j phi and a over 2 e to the j phi. That's the spectrum of the signal x of t. So we're going to spend quite a bit of time studying the spectrum of different signals. So more generally, we can look at the spectrum of a sum of sinusoids. Okay? So any sum of sinusoids we can write as we have at the top of the screen here, right? Where this first term, a naught, that's just a sinusoid at frequency 0, right? It's often just called a DC offset, so it's a constant offset. And then we can represent those sinusoidal signals, each one of those, which has a different amplitude and a different phase and a different frequency. So now a different frequency. We can represent those using complex exponentials. So each term in that sum we're going to represent as using complex exponentials. Now note that I've assumed that all the fk are different. Okay? All the fk are different. And the reason I did that is if there are any two terms in this sum with the same frequency, we already know how to combine those into a single sinusoid at that frequency. So using these complex exponentials, we can get to the second line. The second line just relate A0, that actually just equals A naught, right? And then A sub k, now little a sub k, we've combined this e to the j phi k with ak over 2, and ak conjugate is just going to be ak over 2 e to the minus j phi k. It's written down here. So if we were to go backwards, we could just plug in this guy up here, this guy here, and we'd see that these first and second lines are, of course, the same. When the sum of sinusoids is written in that form, it's really easy to just take out the frequencies and the complex amplitudes, right, for each complex exponential. And if we make a list of those, that's really just the spectrum, often called the two-sided spectrum of x of t. Okay. So in detail, we'd say the first term, the lowest frequency sinusoid is going to be at frequency 0, right? It's the DC component, and that has amplitude A0, and that just equals capital A0. And then the next thing in this list is going to be frequency F1, all right, and complex amplitude A1. I just noticed a typo here. This should be this is also at F1. So the third term in this list, right, is just the term A1 conjugate, which is also at frequency F1. And so on. We make this list of the frequency and the complex amplitude of each sinusoid in the sum, and that would just be the two-sided spectrum of the signal x of t. So that's all there is to making the spectrum of a sum of sinusoids. So let's see that, how we would plot that now. So we have this signal x of t, which we can represent as the sum of a number of sinusoids. And we can represent that as using a list of the complex amplitudes of the sinusoids and their corresponding frequencies, right? And that's the spectrum, okay? This is the spectrum of the signal. It's just a list of the frequencies and the complex amplitudes. So we can plot that, right? We'd start at frequency 0. The signal has an amplitude of A naught. So let me draw that. Whatever that value might be, just say frequency 0, the signal has amplitude A naught. This really kind of tells us the amount of energy that's in the signal at that particular frequency. And then we move on to the next frequency, which again I have a little typo here. This should be F1, right? Because at each frequency there's the positive part and the negative part. Okay? So we're writing these as sums of complex exponentials. All right, so maybe F1 is here. So then minus F1 would be about here. And now I would just maybe have some amplitude this high. And this is going to be A1, right? And this is going to be A1 conjugate. And I'd keep going, and I'd say maybe F2 is here. Minus F2 is down here. Maybe the signal has some amplitude up there. Say A2, and down here we have A2 conjugate. So if we were given this plot where we have all the values of F1, F2, and the corresponding A1, A2, we could of course get A1 conjugate and A2 conjugate. So there's kind of a little redundant information here, but we'd be able to get back to this original sum of sinusoids, right? So somehow the spectrum of the signal contains all the information needed to get back to the time domain signal. So of course, there's more terms here that I didn't draw in both directions. So again, it's pretty simple to go now from this sum of sinusoidal signals to the spectrum of that signal. And then also, if we were given the spectrum of the signal, we could go back to this sum, this time domain signal, and write the signal in the form on the top of the page. So let's see an actual example of that. Well, we have the signal x of t here. Now, it's written as the sum of three things. The first one is just the DC term, or the zero frequency sinusoid. So that's just 7. And that corresponds to, right, we've written A0 before. But that's just equal A0. Right? So right away we could come down to this plot and say at frequency 0 there's going to be a sinusoid with amplitude 7. Right? All right, now the next term, let's just write this whole thing out. X of t, that is going to be equal to 7 plus 8 times 1/2, I'm just using Euler's identity, e to the j, put a parentheses there, 100 pi t plus pi over 4. Remember Euler's identity. Now this is for the cosine, this is just, again, 1/2 e to the minus j, 100 pi t plus pi over 4. Right? So that should be the first cosine here, right? So we've written that first cosine. Now let's write the second cosine just underneath this. This is going to be minus 1/2 e to the j, parentheses, 200 pi t minus pi over 2. Again, plus 1/2 e to the j, e to the minus j, 200 pi t minus pi over 2. Right? So just so everybody knows, right, this first term gave us all this stuff, and the second term, right, that corresponded to all this stuff I have written down here. So we're almost done, right? Just written this signal x of t as the sum of two the sum of. So we're almost done. We've written the signal x of t as in terms of complex exponentials, right? So let's expand this out a little more so we can see exactly what's going on. X of t here, right? So it's going to be 7 plus, now we have 8 times 1/2, which is 4. And now let me factor out the phase, e to the j pi over 4 times e to the j 100 pi t. Right? Now the next term is going to be, again, plus 4. This is 1/2 times 8. E to the minus j pi over 4. E to the minus 100 pi t. Okay. And then down on the bottom, we're just going to have minus 1/2 e to the j 200 pi t. Let me write the phase of that first. So e to the j minus j pi over 2, e to the j 200 pi t, right, minus 1/2 e to the j positive j pi over 2, e to the j minus j 200 pi t. So we've expanded this out in terms of complex exponentials, right? And now we just have each frequency term, it's multiplied by a complex number, right? So we already plotted this 7, right? That was the first thing we did. But we can now come down and plot the rest of the terms. So this first term, right, is at a frequency of how many hertz? It should be 50 hertz, right? So at 50 hertz, so maybe make that there, we have a signal with amplitude 4, and phase e to the j pi over 4, right? But now we also have this next term, and that's the complex conjugate, right? But that's at minus 50 hertz. And again, it should have amplitude 4, but now the phase should be e to the minus j pi over 4. Right? And we're almost done. There's 2 more terms, right? Each one with amplitude 1/2. And those are at 100 hertz. So it's an amplitude 1/2. We're just always going to draw these as being positive. So think of the magnitude of this number, it's still 1/2. So here's 100 hertz, and here's minus 100 hertz. And the signal, the value here is minus 1/2 e to the j pi over 2, right? And here, the positive frequency is minus 1/2 e to the minus j pi over 2. Okay, so that's the spectrum of this sum of a number of sinusoids, of 3 different terms. And remember, we can go back, we can take the signal, the spectrum of x, okay, and we can go back and get the original sinusoidal signal. So if we're given the spectrum, we can go back and forth. It contains all the information to get back up to the time domain signal. So just see very quickly a few real-world examples of this. One that we're all familiar with is FM radio. So the FM band in radio. If you think of this, a lot of times in the older radios, you'd actually have a dial, and you could move the dial around and select a particular frequency. If you were to just look at the spectrum of the FM band, you'd actually, you'd have at different radio stations, you'd have different sinusoids. There'd be some perturbations around those, which we'll learn about later on, but in some interpretations, just think of this as having all these sinusoids at these different frequencies, okay? And maybe they have different amplitudes depending on the strength of the radio station, how close you are. So another application that comes up a lot in electrical engineering is there's something called a spectrum analyzer. And the way this works is it has an input here, okay? And you can hook, a lot of times maybe you'd hook an antenna up to this. So the antenna would be something like this. And then you'd pick up an over-the-air signal. A signal would come in, and that signal, right, would likely be represented well by a sum of sinusoids, and then you'd see something on the screen that would just tell you the frequency and the amount of energy at each particular frequency, which is what is showing on the screen of the spectrum analyzer right now. So each one of these peaks here corresponds to a different signal at a different frequency, okay? And there's a bunch of energy at those frequencies.